Okay, so since the last talk was 2 conferences ago, I'm going to start with a bit of a review of what I did so far. So, review. And so the definition was a generalized fluid system. GRS is RE, E Euclidean, R indeed finite, spanning, spanning set, the span of is E, as I commented numerous times, this is totally superficial. And the second condition is the angle property. Which is if alpha beta, I'm referring here to elements of R, is positive, then alpha minus beta is in R. If it is negative, then alpha plus beta is in R. And if it is 0, then alpha plus beta is in R, different only alpha minus beta. So this is the angle property. As I stated, last time, and then the statement was making slightly stronger and more precise, and I verified it's correct. Even defining this condition, so this condition is just for convenience. And strange enough, even defining this condition is superficial in the sense that if I require that R is just discrete, it would immediately imply that either R is the whole lattice, here lattice in the sense of a free abelian group, or R is finite. So the only thing that finite, defining this condition excludes here is the whole lattice, which is obviously not interesting. And requiring it is discrete is an obvious requirement because if it's not discrete, I can get huge. So, okay. And what I stated last time, and I explained, is that generalized fluid systems have a lot of the properties of fluid systems. And I'm going to actually list what I mean by this. So, for example, you can also have positive systems. Positive system in a root system is a set that is closed on the addition. Closed in the sense that if I have 2 elements whose sum is still a root, and they're in the set, the sum must be in the set. And also, it doesn't intersect its opposite, and together with its opposite, it covers the whole space. Positive systems, basis, the same definition as the definition for root systems. This is a base, a set which is a basis of the vector space, and every root is either a non-negative or a non-positive combination of roots in the simple roots in the basis.
Simple, but definition goes to
the elements of the base. Simple roots is the elements of the base. The poset positive roots. So if I have a positive system or a base, they are the same thing. The poset of positive roots is a very nice lattice with join and meet. The meet is given explicitly. I can reach the 2 roots, one dominating the other one, I can go from one to the other by adding simple roots one at a time and so on and so forth. These are all very, very important. In particular, strings are uninterrupted. This means if I have two roots alpha and beta, and I consider all the roots that are obtained by adding multiples of alpha to beta. So this means I have things like beta minus k alpha, beta minus k minus 1 alpha, beta plus alpha, beta plus s alpha. So because this is a finite system, if I consider all the roots of the form beta plus integer alpha, it would be a finite set, and the claim is it is a whole interval. It's not continuous. And this allows me to define sigma alpha from R to R, which is reverses all alpha strings. So this means that I'm taking this, and sigma alpha of beta plus S alpha is beta minus K alpha. Sigma alpha of beta plus S minus 1 alpha is beta minus K minus 1 alpha, and so on. Just reverse that. Here I'm assuming alpha is primitive. Primitive means, this is one of the differences, that no multiple of alpha is a root other than minus alpha and 0. 0 is always a root in my definition, so the only multiples of roots. In fact, one can define sigma alpha even if alpha is not primitive, but it's unnecessary. So, and now this was a question that I still don't have an answer. I don't know. Does the group sigma alpha and alpha primitive? Have good role. Sure. So this is very open. The question is, because I can define here permutation of the roots for every alpha, I can consider all the group generated by these permutations. It's a well-defined group. The question is, does it do anything meaningful? I don't know, and I have never actually looked at this question.
Can I ask about this
Yeah.
primitive? Something became unclear, like if alpha and 2 alpha are roots, none of those is primitive.
Alpha is a root. No. Yes, sorry, fractions of alpha are roots. If alpha and 2 alpha is,
okay.
I apologize.
Okay, very
I
good.
apologize.
Okay, very good.
Primitive
So
means fractions are root.
Okay.
I said it incorrectly.
Fractions are not roots.
Yeah, fractions
Instead
are
of
roots.
multiples.
Instead of multiples, I apologize. Thank you for pointing. Yeah. Fractions are root. So what happens is now, this allows you to define the viable groupoid. Whose objects are just the positive systems. And the homes are just these reflections, but carefully applied. So homes for a positive system P with base S, if alpha is in the base, then sigma alpha P is the positive system. With base sigma alpha. But in order to claim this, I have to assume that alpha is a simple root for this process. And these are the hops. And then obviously involved.
So this would be very different notion from the notion of Weyl groupoid in the area of Nichols algebra.
Yeah.
It's completely different.
But I have a different, I have a suggestion for different definition of Weyl groupoid. This is the standard one that was used for proving the classification theorem.
Okay.
That comes in the works of people that consider what they call Weyl groupoids and hyperplane arrangements. Unless I will propose something else.
Because even for type A, this is just the Weyl group. This is not the Weyl group.
It's not the Weyl group, it has way too many objects. So it actually has no Weyl group. This Weyl groupoid has no Weyl group. The group of a groupoid is just the group of every homes from an object to itself.
The vertex group.
Yeah.
So this is probably going to be another question, but how are we sure that sigma alpha p is the generalized system? It might be obvious, but I'm not seeing.
No, sigma alpha is a positive system.
Yes, okay.
Positive system. I'm using system in two different ways. The generalized root system, everything is happening in the fixed generalized root system R. A positive system is a subset of positive roots.
Okay.
So I'm saying that this is a positive system. If everything is still happening, positive system is in R. Everything is happening in the same R.
And how are we sure that this is a positive system?
Well, we proved it.
Okay.
Yeah. I mean, these proofs are really elementary. Most of them are basically parallel to how we prove things for root systems. And I'm just rather,
It's not something complex.
yes. It's very easy to write what sigma alpha is and set it from there. What sigma alpha does is takes all the p's, removes alpha, except now if alpha is not, if alpha has multiples, it removes all the positive multiples and adds the negative multiples. Just switches alpha.
Okay, so if this is just the root system, not the generalized.
Yeah.
This will be a reflection just like well.
Exactly, this is the reflection with respect to alpha. Yeah. Of course.
Okay.
The only difference is that here, even though I define sigma alpha independent of a positive system, I only apply sigma alpha to positive systems for which alpha is a simple. Even in the usual root systems, if you take base,
Okay.
right, and take a root that is not simple, the reflection with respect to the non-simple root messes things up.
Yeah.
You don't have such an answer. Yeah. And here I'm just careful of.
Okay.
So these are the forms, and the main claim here is that any two positive systems, equivalent bases are linked by a chain of century. And this is well known fact for root systems, that the Weyl group acts simply transitively on positive, on basis, this form. So this is what we did last time. Just one remark about sigma alpha. Sigma alpha doesn't even have to be a linear, it doesn't have to be linear in the sense that I'm defining it on the set R, and I'm asking, does it extend to a linear transformation of the vector space? Now, R is not a basis, R is just a spanning set, and sigma alpha may not even be a linear transformation. Not only is it not an isometry, always.
Okay.
Sometimes it is an isometry, sometimes it is linear. And this is actually very much related to another thing that I need to remind you, is isomorphism. And so R prime E prime is isomorphic to R double prime E double prime. If there is um, not isometry, but I want here, there is, what's the name for preserving angle? Conformal. There is a conformal linear transformation phi from E prime to double prime, such that phi of R prime equals R double prime. This is saying essentially it's an isometry, but of course on the different components I can scale by different things. And R prime E prime is equivalent if there is a linear transformation phi over 1. So if I have a linear transformation that is bijection between R prime and R double prime, this is equivalence. If this linear transformation also preserves the angles, it is an isomorphism. So the example here was in rank 2. Rank means, of course, the dimension of the vector space C. I have these root systems. Just looking like A2. Put them, I don't name them, just put them in A2 in quotation marks. As long as the angles between alpha and beta, the angle is austrial, and the angles between alpha plus beta, and beta alpha plus beta are equal, this is a root system. It satisfies a generalized root system. This is equivalent to A2, but not isomorphic. Because the relative lengths of alpha and beta may not be the same, the length may not be the same, and the angle doesn't have to be exactly 120 degrees. So, I want to say something about the first attempt. So far I have introduced something, and I have stated that it extends the properties of root systems. But actually, the main thing is, are there such things? I mean, obviously root systems are such things, but beyond root systems, maybe there is nothing. So maybe this is just an empty exercise. And so let's look at GRSs of small rank. Small rank means 1 is 2. And I'm not going to go with them all. I'm just going to say that there is a classification, and it's much richer than just root systems. First, if the rank of R is 1, this is something we discussed last time, then R is just a string alpha to alpha, nothing else. If the rank of R is two and R is irreducible, as with root systems, of course, if I take two generalized root systems in two spaces and take the direct sum of these two spaces, orthogonal direct sum, and take their union, this will be a generalized root system. It is irreducible, it cannot be decomposed like this. There is a theorem that every generalized root system decomposes uniquely as the product of irreducibles. So if it is irreducible, last time we saw that R reduced. So here, I must say that I don't feel so bad for not coming up with a reasonable name for these objects and calling them GRSs, because this is also pretty terrible. Reduced and irreducible refer to totally different things. Irreducible means that it cannot be put into two mutually orthogonal subspaces. Reduced means that you cannot have multiples of a root being root. Right. This is already a condition for root systems, and if one does not require root systems to be reduced, there is another series of simple root systems, namely BC, and the root systems that like B and C, but have both the short and the long roots and middle. So if it's reduced, last time you saw that there are three of them, namely A2, which I gave here. This actually depends on two continuous parameters here. There is a B2 that depends on one parameter because there is one rigidity condition, and there is G2, which is always G2. I cannot actually break it. But now I want to go beyond the reduced because one of the major differences between generalized root systems and root systems is that I have multiples of root being roots. And so let me define the multiplier MR of R is the largest M for which there are roots alpha, 2 alpha, 3 alpha, M. So multiply is the largest possible thing that by which I can multiply. So for rank 1, for this system, the multiplier is key. And here is the theorem, which is a classification theorem. I'm going to write it up to equivalence, even though one can do it up to isomorphism, but it is just ugly. Up to equivalence, there are I'm going to fill in this number when I write down the whole thing. Irreducible root systems, generalized root systems. Okay. And I'm going to write the number by the multiplier. M number with this multiplier. 1, 2, 3, 4. We already saw that there are 3 rank with multiplier 1. There are 8 with multiplier 2. There are 4 with multiplier 3. And there is 1 with multiplier 4. And that's all. So if the rank is not 1, the multiplier is going by 4. And this is the one. And they can be explicitly written.
And probably after 5 is all 0.
Yeah. the multiplier, so the first part of the theorem would be MR is less or equal than. Here is an example of something with multiplier 3. I'll erase a little bit here and it is 1. I'll write it here as a set and then I'll draw it. 0 plus minus x plus minus 2x plus minus 3x plus minus y plus minus y plus minus x plus minus y plus minus 2x plus minus 2y plus minus x plus minus 2y plus minus 2x and plus minus 3y. Where x is orthogonal to y and the length terms. So they look like this. 0 here, x, 2x, 3x, so minus x, minus 2x, minus 3x, y twice, 3 times. Beautiful. So it's a very, very kind of nice symmetrical thing. Here, this is x, this is y.
There is one dot missing.
Okay. It will take you probably 3 or 4 minutes to verify this. Notice that I can consider several bases. So, for example, x and y minus 2x is a base, S1. X and y minus 2x is a base. S2, which is minus x and y plus 2x is a base. And S3, which is minus y minus 2x and x plus y, these are all bases. So draw it. So the second one is this one. And the third one is this one. There is nothing mysterious about this. S2 is sigma of x S1. I flipped through this one and all the rest of it. And S3 is sigma of y plus 2x of S1.
Then there are more. I mean,
There are more.
yeah.
There are more. I can feel now, I can flip here, this one, and I'll get minus x plus y, and this one, which is 2y plus x, and so on. And I want to go back here to extend this definition, to extend it to extend to R prime, E prime, S prime versus R double prime, E double prime, S double. What I mean by versus, here this is a generalized root system with a base, and another generalized root system with a base, and I'm going to require here that phi S goes to X, not just phi of S prime equals S prime. And I wrote versus because I will both consider isomorphic and equivalent. Isomorphic would mean distal isometry and equivalence would mean. So if you look at these two, these are isomorphic. And these are not even equivalent. This takes a little bit more work. And it's related to the fact that sigma x here is in fact an honest reflection. I'm just flipping, see, these are my x strings, and I'm flipping them over. This is exactly the reflection about the y-axis. But if I take y equals 2x, this string I'm flipping, this string here looks like this, the next string looks shifted, and if I flip each one of them, this doesn't come from a linear transformation. And equivalence of these bases is the same as linear transformation, as morphism is the same as really reflection. So this is just an example. Most of the time, I'm going to look at S prime isomorphic to S double prime or S prime equivalent to S double prime where they are bases in the same root system. I'll be looking at one root system, different bases. So this is what this is about. If you look at this example, you're going, as you mentioned, there are more positive systems. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Maybe 16, if I'm not mistaken.
The task then would be to see which of them I could.
Exactly. And in this case, actually, there are two isomorphism, not just equivalence, there are two isomorphism classes. This is one, and yeah. And preview for the about the point. I don't want my objects to be all the Borels, but all the sorry, not Borels positive systems, but all bases up to isomorphism. So this one would have only two objects. And the value and the group of vertex will be meaningful. Right. Okay. So this is the expanded review of what I did so far. Though I stated this theorem about rank 2. I'm not going to delve into the classification here. The only thing that I want to say is that this is kind of both good news and bad news. Good news because we are getting new objects compared to root systems. Bad news seems like the standard approach to classification, where we use that there is only one rank 1 root system, and there are only 3 rank 2 root systems. Here I have what is this, 16? Yeah, 16. So if I try to do similar combinatorics, it will be a nightmare. Because if I try to write down even a diagram, thinking diagram singular, my vertices would be different depending on what the A1 system is corresponding to the rank 1. They can be either with multiplier 1, 2, or 3, or 4, and my edges would be different. The edges would be one of these 16 things.
How would the diagram look for a multiplier diagram one?
Sorry?
How would the diagram look? So what would it look like for a multiplier diagram one?
I don't think it's useful, so yeah. However, there is actually a classification result, and I'll explain all of these in the online. So there is no need now to actually.
Okay, let's just say, curious.
Yeah, I don't have a good notion of it. Okay, so let me continue with the main reason we introduced roots for these generalized processes. So, caution. So assume R is RE is the generalized on system with base S. And I take a subset of S. I take a subset of people root. I'm going to use this mostly out of habit, and because this is a convenient notation, I'll make a remark that actually the definition is a bit more invariant than choosing a particular base and particular subset. But it's immaterial. The notation, however, is very convenient here. Then I can define EI to be the span phi, just the subspace span phi, and E by I to be the orthogonal complement of I. So why is it quotient? Because I have from E decomposing as EI plus EI orthogonal complement. I have phi I, the orthogonal projection of E to E to this orthogonal complement that I just know. And then I define Ri, the intersection of EI with R. This is a subsystem. Obviously, it's abstract. And I define R mod I to be phi I, the projection of the whole system. And the theorem, which is not awfully difficult, is theorem. The subsystem is a generalized root system in EI with base I. That's all very interesting. R mod I, E mod I is a generalized root system with base phi I S except 0. I have to. So it's very canonical. And for root systems, we have none. There is no choice. Now properties punctuality. Clearly it is punctual in the sense that if I take I in J in S, R mod I by J mod I. This is more to R mod G. Now, the proof is very simple. It's just by the definition, but let's see that we know what we're writing. R mod I is a root system, is a generalized root system in the space S mod I, which has basis. This system has basis S mod I. J mod I is the subset of S mod I. Hence, I'm taking a generalized root system and the subset of simple roots. I'm taking this quotient and I'm getting it. So, that's it. Okay, next thing we want to say. Comment. This construction does not depend on I. It depends on the spanner. So, the construction does not depend on I, but on the W, which is the spanner. I denoted W before as EI, but here, because I'm making a different point, I would denote it by W. So as long as I take a subspace, so any W, any subspace W in E spanned by roots works. So notice it is not any subspace. If I just take arbitrary subspace and project onto that, that won't work. But if it is spanned by roots, then it is the same situation, because if I intersect and take in this subspace the subsystem, it is a generalized root system, hence it has a base. This base can be extended to a base of the whole root system, and then I'll construct it from that base, and I'll get exactly the same. So really the dependence is on a subspace, but the subspace has to be special. Has to be standard. And because of this kind of statement and further statements about rejection between bases of one and the other, I find it convenient to assume that I have fixed the base. So it is really about a subspace of about the base. Now, an actual question is, can we use a more general W? And the answer is that I don't know how general subspace I can use. However, so the first abstraction would be, if you think of the root lattice and consider the projection of the root lattice onto W, it may preserve its rank, or it may not drop its rank as much as the dimension of the space drops. And that would be an abstraction. But that's not the only thing. There are other abstractions in which I take a subspace, project, and then the angle property is lost. So there is something important about the angle property that is guaranteed in this case. However, interestingly enough, I know one more case in which it works. So the answer is I don't know. But it also works for the fixed points. For W being the fixed points of a diagram of Morrison of Dell. So if I start with the root system, consider diagram automorphism, extend it to a linear transformation, consider the fixed points of this linear transformation, and then project onto that. It actually works. And what happens is this, we get the twisted delta theta, except almost we get the union of the fixed points and the points that are. So in particular, what happens here is, you know that I can twist almost a little bit of space. So what is happening here is if I take DL and take this diagram also, the resulting delta zero take is DL minus one, and delta one theta is short root. And if I add them together, if I take them union, I only get B. If I take D4 and take this diagram of Morrison, I get delta zero theta is G2, and delta plus minus one theta is short. Okay. When I take them, take the union, I only see the G2. If I take E6, I get F4, sorry, F4. And again, the short roots of F4, hence when I take the union, I don't get it. No? When I take AL 2L plus 1, and take the automorphism, I get CL plus 1 plus short roots, which when I take the union, I only get CL. And I got to my punchline finally. If I take A2L, I get delta theta 0 is PL, but delta theta 1 is the roots. Delta theta 1 is the weight of S squared of the natural representation. So when I take the union, I get the system BCL. So this is one thing that is annoying and kind of always bothered me. Why the twisted? If I mean, if you're looking at this level, you'd be thinking, how do I get BL by twisting? Do I get it from TL or from A to L? But the truth is, you get it from DL, from A to L, you're getting BC, not B. Yeah. Any questions? So this is a question that I have not explored any further. I don't know the answer. But I like the idea that we can think of listing as actual also projection, except it doesn't distinguish between the zero and two.
What was the meaning of 0 and 1?
This is an automorphism, right? For the two. Zero are the fixed points, and one are the points that are centered there off. The eigenspace with eigenvalue one dimension. And here I wrote 0 plus minus 1 because it's for the 3. So I have eigenvalues 1 and the other two cubic roots. Hmm?
Yeah.
Yeah. So a little bit more about quotients. I already stated that the quotient is functorial. It actually behaves well with respect to bases as well. So consider R E I S is above. So the question is, what are the bases of the quotient? T in R mod I is a base of R mod I. Actually, exactly the most material thing that we would expect, if and only if they exist a base S prime of R, S prime containing I, such that P is S prime by I. So the bases are exactly. The bases are exactly proportional. Exactly.
And in this case, it's somehow more complicated, right? When you do those kind of projections.
No, this is similar. In this case, I know.
In
I
this
cannot-
case, it's,
yeah.
it's more.
Yeah, because it is not such a.
Mhm.
These values, these fixed points are not spanned by roots, and so it is more complex.
Mhm.
So this is only in this construction.
Right.
And finally, I have 5 minutes left. I'm going to discuss the fibers. Phi I from R to R mod I. So, what do I mean here? The obvious thing, let mu be in R mod I, then define R nu to be the pre-image, the fiber. There's some strange mechanics involved in the
Anti-gravity.
Hmm?
Anti-gravity.
Yeah. Starting somebody in massive people.
Somebody.
Upstairs.
Speak gravity.
Yeah. Okay, so now, I want to discuss our new, because it is in the primitive, phi I, I'm going to consider this, how should I say, in our new, we define partial order, beta prime, less than beta double prime, if beta double prime minus beta prime is the sum C alpha 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 in I C alpha non-negative. So because they are in the same cycle of I, the difference between the two is integral combination of elements of I. And if these elements are non-negative, I say that beta double prime dominates beta prime. This is a partial order.
Do you know that for every pair of roots, if you write it like this, then all C alpha will have the same sign?
No. No, this is the fiber there.
Mhm.
It is a partial order. So the statement is that R nu is a lattice or actually this is even better than the whole R plus. Nu not the fiber over. Here all the lead and the join are given by the right formula. Here, beta prime is the sum A alpha prime alpha. S. Yes. Alpha. So what I'm saying is, if they're in the same fiber, the coefficients of beta prime and beta double prime, the primes come from beta double prime, are the same outside the phi. They only differ in I, right? So I'm not saying anything by taking the minimum and the maximum if alpha is not in I. And if alpha is in I, I'm generally taking the small or the large. And this is similar. This is the same formula held in R plus, but this formula does not hold in R plus. However, it holds in the fiber. This is the first thing. The second thing is R nu have smallest and the largest element. Both smallest and largest with respect to this order. And the third thing is the Casa diagram. Are no utility.
So is it going to hold for all roots that have been done?
Sorry?
Is it going to hold for all roots? So because Okay, I is subset of your base.
Yeah, so you're saying if I is M, what am I saying if I is M?
Well, I was gonna, so the positivity of the efficiency alpha, this is what bothered me. So if you have roots which are negative combinations of alpha, so, yeah.
No, I'm defining disorder in this way. I'm defining, it's a partial,
Is it a partial root beta? This is the question that I was.
it's a partial order.
Okay.
It's only a partial order.
Yeah, said.
So it's not a total order. So some of them will be negative. If some of them are positive, some of them are negative, then they are not defined.
But can you not have like, so obviously since it is a base, is it true that every root can be represented as some like this C alpha time alpha?
This
We either C alpha positive or negative.
yeah.
Yeah, so why not do this splitting here as well? Why not consider the two combinations? So do you not have an order like, because obviously this is ordered by height of the roots, right?
No, not by height, not by height. So
Okay.
in B4, let's see if B2 gives us the G2 certainly give us the, so let's look at G2. So from here, I want to subtract the root, so I'm writing the Hasse diagram of the positive.
Okay.
From here, I want to subtract this root, I cannot, goes down here, here, and from here. There's the Hasse diagram.
Can you explain your diagram because it somehow happened too quickly? What is I? Can you explain your diagram? What is I? I is the whole S? Fine.
No, I is subset.
No, in the example, what is I?
Oh, in this example, it's the whole.
Yeah, if you could.
Yeah, this is the host.
I guess the statement is that if you have two roots and one has bigger height than the other, doesn't mean that they're related by a chain of simple roots.
Though this is not an example.
So the highest root will be higher than most, but it doesn't mean that if you have in some big system, you have a root of height 2 and a root of height 1. They're not related, they're far away from each other.
You mean when the alpha is partial order will not solve the,
Yeah.
I think I understand.
Yeah.
Yes, but.
Okay. Let me say what this theorem is saying. This theorem is giving the purely combinatorial truth of the theorem constant. So, and this will be.
So this difference alpha is an I or S?
In this difference, alpha is in I, here it is in S. It is necessarily in I, the difference, because they have the same projection. So if I write beta prime equal some alpha in S, A alpha double prime alpha, then I know that A alpha prime equals A alpha double prime for alpha one zero. Because they are in the same file. So that's why
Yeah, we're taking coverage here, so we get, so you start at the RV, we define. So this partial is defined in RV, which obviously means that we have to take I.
yeah. Good. So here is what this theorem is saying, actually. And this is what I'll add. Let should be a simple out, right? T diagonal surbounds, right? So to get the root decomposition, I need to take a Cartan surbound, which is the maximum top. Here I'm taking just a total. Then G decomposes as M plus the sum G mu, mu in T star minus 0. I want to separate this. I want to separate the 0 and and I assume that T equals the center. Then, under these conditions, the set R of nu such that R mu is not below. is equal delta by I, where I is the base of M, which is a reductive subalgebra. So I'm taking a simple algebra. M is a reductive subalgebra, a Levy reductive or special reduction. Levy. Here's M, the roots of M form a sub system of the whole root system. And this is exactly the quotient root system here. Okay. And Costas theorem says that G nu is an irreducible M1. And I'm saying, how to go, what is G nu? G nu consists of all the root vectors that project onto nu. So I'm taking all roots that project onto nu. And I'm saying that I can link any two of them by a sequence of simple roots. But because in a linear algebra, if I commute two root spaces and the sum of these two roots is still a root, the commutator of these root spaces is non-zero. Hence, the combinatorial statement here provides a pure combinatorial proof. And I will stop here, and next time I'll discuss the quotients of root systems. Actually, the statement is that every generalized root system is equivalent to a quotient of a root system, and then talk about quotients and talk about these reflections, how they are read of root systems, and this will be.
Any questions for third lecture 31? Okay, then we will stop here. Let's thank Ivan again.